Chapter 20 of Astronomy, The Science of the Heavenly Bodies, by David Todd. Chapter 20, The Story of the Spectroscope. Sir Isaac Newton really ought to have been the inventor of the spectroscope, because he began by analyzing light in the rough with prisms, was very expert in optics, and was certainly enough of a philosopher to have laid the foundations of the science. What Newton did was to admit sunlight into a darkened room through a small round aperture, then pass the rays through a glass prism and receive the band of color on a screen. He noticed the succession of colors correctly: violet, indigo, blue, green, yellow, orange, red. Also that they were not pure colors, but overlapping bands of color. Apparently neither he nor any other experimenter, for more than a century, went any further when the next essential step was taken by Wollaston about 1802 in England. He saw that by receiving the light through a narrow slit instead of a round hole, he got a purer spectrum. Spectrum being the name given to the succession of colors into which the prism splits up or decomposes the original beam of white sunlight. This seemingly insignificant change, a narrow slit replacing the round hole, made Wollaston, and not Newton, the discoverer of the dark lines crossing the spectrum at various irregular intervals, and these singularly neglected lines meant the basis of a new and most important science. Even Wollaston, however, passed them by, and it was Fraunhofer who, in 1814-15, first made a chart of them. Consequently, they are known as Fraunhofer lines, or dark absorption lines. Sending the beam of light through a succession of prisms gives greater dispersion and increases the power of the spectroscope. The greater the dispersion, the greater the number of absorption lines. And it is the number and intensity of these lines, with their accurate position throughout the range of the spectrum, which becomes the basis of spectrum analysis. The half-century that saw the invention of the steam engine, photography, the railroad, and the telegraph elapsed without any farther developments than mere mapping of the fundamental lines A, B, C, D, E, F, G, H of the solar spectrum. The moon, too, was examined, and its spectrum found the same, as was to be expected, from sunlight simply reflected. Sir John Herschel and other experimenters came near guessing the significance of the dark lines, but the problem of unraveling their mystery was finally solved by Bunsen and Kirchhoff, who ascertained that an incandescent gas emits rays of exactly the same degree of refrangibility which it absorbs when white light is passed through it. This great discovery was at once received as the secure basis of spectrum analysis, and Kirchhoff in 1858 put, in compact and comprehensive form, the three following principles underlying the theory of the science. 1. Solid and liquid bodies, also gases under high pressure, give, when incandescent, a continuous spectrum, that is, one with a mere succession of colors, and neither bright nor dark lines. 2. Gases under low pressure give a discontinuous spectrum, crossed by bright lines whose number and position in the spectrum differ according to the substances vaporized. 3. When white light passes through a gas, this medium absorbs, or quenches, rays of identical wavelength with those composing its own bright line spectrum. Clearly, then, it makes no difference where the light originates, whether it comes from sun or star. Only it must be bright enough so that we can analyze it with the spectroscope. But our analysis of sun and star could not proceed until the chemist had vaporized in the laboratory all the elements and charted their spectra with accuracy. When this had been done, every substance became at once recognizable by the number and position of its lines with practical certainty. How then can we be sure of the chemical and physical composition of sun and stars? Only by detailed and critical comparison of their spectra with the laboratory spectra of elements which chemical and physical research have supplied. As in the sun, so in the stars, each of which is encircled by a gaseous absorptive layer or atmosphere The light rays from the self-luminous inner sphere must pass through this reversing layer, which absorbs light of exactly the same wavelength as the lines which make up its own bright line spectrum. Whatever substances are here found in gaseous condition, the same will be evident by dark lines in the spectrum of sun or star, and the position of these dark lines will show, by coincidence with the position of the laboratory bright lines, all the substances that are vaporized in the atmosphere of the self-luminous bodies of the sky. Here then originated the science of the new astronomy. The old astronomy had concerned itself mainly with positions of the heavenly bodies, where they are. The new astronomy deals with their chemical composition and physical constitution and what they are. Between 1865 and 1875, the fundamental application of the basic principles was well advanced by the researches of Sir William Huggins in England, of Father Angelo Secchi in Rome, of Jules Janssen in Paris, and of Dr. Henry Draper in New York. In analyzing the spectrum of the sun, many thousands of dark absorption lines are found, and their coincidences with the bright lines of terrestrial elements show that iron, for instance, is most prominently identified, with rather more than 2,000 coincidences of bright and dark lines. Calcium, too, is indicated by peculiar intensity of its lines, as well as their great number. Next in order are hydrogen, nickel, and sodium. By prolonged and minute comparison of the solar spectrum with spectra of terrestrial elements, something like 40 elemental substances are now known to exist in the sun. Rowland's splendid photographs of the solar system have contributed most effectively. About half of these elements, though not in order of certainty, are aluminum, cadmium, calcium, carbon, chromium, cobalt, copper, hydrogen, iron, magnesium, manganese, nickel, scandium, silicon, silver, sodium, titanium, vanadium, yttrium, zinc, and zirconium. Oxygen, too, is pretty surely indicated, but certain elements abundant on Earth, as nitrogen and chlorine, together with gold, mercury, phosphorus, and sulfur, are not found in the sun. The two brilliant red stars, Aldebaran in Taurus and Betelgeuse in Orion, were the first two stars whose chemical constitution was revealed to the eye of man, and Sir William Huggins of London was the astronomer who achieved this epoch-making result. Father Secchi of the Vatican Observatory proceeded at once with the visual examination of the spectra of hundreds of the brighter stars, and he was the first to provide a classification of stellar spectra. These were the four types. Secchi's type 1 is characterized chiefly by the breadth and intensity of dark hydrogen lines, together with a faintness or entire absence of metallic lines. These are bluish or white stars, and they are very abundant, nearly half of all the stars. Vega, Altair, and numerous other bright stars belong to this type, and especially Sirius, which gives to the type the name Sirians. Type 2 is characterized by a multitude of fine, dark, metallic lines, closely resembling the lines of the solar spectrum. These stars are somewhat yellowish in tinge, like the sun, and from this similarity of spectra, they are called solars. Arcturus and Capella are solars, and on the whole, the solars are rather less numerous than the Sirians. Stars nearest to the solar system are mostly of this type, and according to Kapteyn of Groningen, the absolute luminous power of the first type stars exceeds that of the second type stars sevenfold. Secchi's type 3 is characterized by many dark bands, well defined on the side towards the blue end of the spectrum, but shading off toward the red. A colonnaded spectrum, as Miss Clerk aptly terms it. Alpha Herculis, Antares, and Mira, together with orange and reddish stars, and most of the variable stars, belong in type 3. Type 4 is also characterized by dark bands, often called flutings, similar to those of type 3, but reversed as to shading, that is, well defined on the side toward the red, but fading out toward the blue. Their atmospheres contain carbon, but they are not abundant, besides being faint and nearly all blood red in tint. Following up the brilliant researches of Draper, who in 1872 obtained the first successful photograph of a star's spectrum, that of Vega, Pickering of Harvard supplemented Secchi's classification by type 5, a spectrum characterized by bright lines. They too are not abundant and are all found near the middle of the galaxy. These are usually known as Wolf-Rayet stars, from the two Paris astronomers who first investigated their spectra. Type 5 stars are a class of objects seemingly apart from the rest of the stellar universe, and many of the planetary nebulae yield the same sort of a spectrum. The late Mrs. Anna Palmer Draper, widow of Dr. Henry Draper, established the Henry Draper Memorial at Harvard, and investigation of the photographic spectra of all the brighter stars of the entire heavens has been prosecuted on a comprehensive scale. Those of the northern hemisphere at Cambridge, and of the southern at Arequipa, Peru. These researches have led to a broad reclassification of the stars into 8 distinct groups, a work of exceptional magnitude, begun by the late Mrs. Fleming and recently completed by Miss Annie Cannon, who classified the photographic spectra of more than 230,000 stars on the new system as follows. The letters O, B, A, F, G, K, M, N represent a continuous gradation in the supposed order of stellar evolution, and farther subdivision is indicated by tenths. G5K, meaning a type halfway between G and K, and usually written G5 simply. B2 would indicate a type between B and A, but nearer to B than A, and so on. On this system, the spectrum of a star in the earliest stages of its evolution is made up of diffuse bright bands on a faint continuous background. As these bands become fewer and narrower, very faint absorption lines begin to appear. First the helium lines, followed by several series of hydrogen lines. On the disappearance of the bright bands, the spectrum becomes wholly absorptive bands and lines. Then comes a very great increase in intensity of the true hydrogen spectrum, with wide and much diffused lines, and few, if any other, lines. Then H and K calcium lines and other lines peculiar to the Sun become more and more intense. Then the hydrogen lines go through their long decline. The calcium spectrum becomes intense, and later the spectrum becomes quite like that of the Sun, with a great wealth of lines. Following this stage, the spectrum shortens from the ultraviolet, the hydrogen lines fade out still farther, and bands due to metallic compounds make their appearance, the entire spectrum finally resembling that of sunspots. To designate these types rather more categorically, type O, bright bands on a faint continuous background with 5 subdivisions: OA, OB, OC, OD, OE, according to the varying width and intensity of the bands. Type B, the Orion type or helium type, with additional lines of origin unknown as yet, but without any of the bright bands of type O. Type A, the Sirian type, the regular Balmer series of hydrogen lines being very intense, with a few other lines not conspicuously marked. Type F, the calcium type, hydrogen lines less strongly marked, but with the narrow calcium lines H and K very intense. Type G, the solar type, with multitudes of metallic lines. Type K, in some respects similar to G, but with the hydrogen lines fading out and the metallic lines relatively more prominent. Type M, spectrum with peculiar flutings due to titanium oxide, with subdivisions MA and MB, and the variable stars of long period with a few bright hydrogen lines additional in a separate class, MD. Type N, similar to M, in that both are pronouncedly reddish, but with characteristic flutings probably indicating carbon compounds. The Draper classification being based on photographic spectra, and the original Secchi classification being visual, the relation of the two systems is approximately as follows. Secchi type 1, includes Draper B and A. Secchi type 2 includes Draper F, G, and K. Secchi type 3 includes Draper M. Secchi type 4 includes Draper N. Pickering's marked success in organization and execution of this great program was due to his adoption of the slitless spectroscope, which made it possible to photograph stellar spectra in vast numbers on a single plate. The first observers of stellar spectra placed the spectroscope beyond the focus of the telescope with which it was used, thereby limiting the examination to but one star at a time. In the slitless spectroscope, a large prism is mounted in front of the objective of short focus so that the star's rays pass through it first and then are brought to the same focus on the photographic plate for all the stars within the field of view, sometimes many thousand in number. This arrangement provides great advantages in the comparison and classification of stellar spectra. When spectroscopic methods were first introduced into astronomy, there was no expectation that the field of the old or so-called exact astronomy would be invaded. Physicists were sometimes jocularly greeted among astronomers as ribbon men, and no one even dreamed that their researches were one day to advance to equal recognition with results derived from micrometer, meridian circle, and heliometer. The first step in this direction was taken in 1868 by Sir William Huggins of London, who noticed small displacements in the lines of spectra of very bright stars. In fact, the whole spectrum appeared to be shifted. In the case of Sirius, it was shifted toward the red, while the whole spectrum of Arcturus was shifted by 3 times this amount toward the violet end of the spectrum. The reason was not difficult to assign. As early as 1842, Doppler had enunciated the principle that, when we are approaching, or are approached by, a body which is emitting regular vibrations, then the number of waves we receive in a second is increased, and their wavelength correspondingly diminished, just as the reverse of this occurs when the distance of the vibrating body is increasing. It is the same with light as with sound, and everyone has noticed how the pitch of a locomotive whistle suddenly rises as it passes and falls as suddenly on retreating from us. So Huggins drew the immediate inference that the distance between the Earth and Sirius was increasing at the rate of nearly 20 miles per second, while Arcturus was nearing us with a velocity of 60 miles per second. These pioneer observations of motions in the line of sight, or radial velocities as they are now called, led directly to the acceptance of the high value of spectroscopic work as an adjunct of exact astronomy in stellar research, nor has it been found wanting in application to a great variety of exact problems in the solar system which would have been wholly impossible to solve without it. Foremost is the sun, of course, because of the overplus of light. Young early measured the displacement of lines in the spectra of the prominences and found velocities sometimes exceeding 250 miles per second. Many astronomers, Dunier among them, investigated the rotation of the sun by the spectroscopic method. The sun's east limb is coming toward us, while the west is going from us, and by measuring the sum of displacements, the rate of rotation has been calculated, not only at the sun's equator, but at many solar latitudes also, both north and south. As was to be expected, these results agree well with the sun's rotation as found by the transits of sunspots in the lower latitudes where they make their appearance. Belopolsky has applied the same method to the rotation of the planet Venus, and Keeler, by measuring the displacement of lines in the spectrum of Saturn on opposite sides of the ring, provided a brilliant observational proof of the physical constitution of the rings, because he showed that the inner ring traveled round more swiftly than the outer one, thus demonstrating that the ring could not be solid, but must be composed of multitudes of small particles traveling around the ball of Saturn, much as if they were satellites. Indeed, Keeler ascertained the velocity of their orbital motion and found that in each case it agreed exactly with that required by Keplerian law. Even the filmy corona of the sun was investigated in similar fashion by Deslandres looked at the total eclipse of 1893, and he found that it rotates bodily with the sun. But the complete vindication of the spectroscopic method as an adjunct of the old astronomy came with its application to measurement of the distance of the sun. The method is very interesting and was first suggested by Campbell in 1892. Spectrum line measurements have become very accurate with the introduction of dry plate photography, and ecliptic stars were spectrographed toward and from which the Earth is traveling by its orbital motion around the sun. By accurate measurement of these displacements, the orbital velocity of the Earth is calculated, and as we know the exact length of the year, or a complete period, the length of the orbit itself in miles becomes known, and thus, by simple mensuration, the length of the radius of the orbit, which is the distance of the Sun. If we pass from sun to star, the triumph of the spectroscope has been everywhere complete and significant. As the spectroscopic survey of the stars grew toward completeness, it became evident that the swarming hosts of the stellar universe are in constant motion through space, not only athwart the line of vision, as their proper motions had long disclosed, but some stars are swiftly moving toward our solar system, and others as swiftly from it. Fixed stars, strictly speaking, there are no such. All are in relative motion. Exact astronomy, by discussion of the proper motions, had assigned a region of the sky toward which the sun and planets are moving. Spectrography soon verified this direction not only, but gave a determination of the velocity of our motion of 12 miles per second in a direction approximately that of the constellation Lyra. From corresponding radial velocities, we draw the ready conclusion that certain groups or clusters of stars are actually connected in space and moving as related systems, as in the Pleiades and Ursa Major. Rather more than a quarter century ago, the spectroscope came to the assistance of the telescope in helping to solve the intricate problem of stellar distribution. Kapteyn, by combining the proper motions of certain stars with their classification in the Draper Catalogue of Stellar Spectra, drew the conclusion that, as stars having very small proper motions show a condensation towards the galaxy, the stars composing this girdle are mostly of the Sirian type and are at vast distances from the solar system. The proper motion of a star near to us will ordinarily be large, and in the case of solar stars, the larger their proper motion, the greater their number. So it would appear that the solar stars are aggregated round the Sun himself, and this conclusion is greatly strengthened by the fact that, of those stars whose distances and spectral type are both ascertained, 7 of the 8 nearest to us are solar stars. In 1889, the spectroscope achieved an unexpected triumph by enabling the late Professor Pickering to make the first discovery of a spectroscopic double, or binary star, a type of object now quite abundant. Unlike the visual binary systems, whose periods are years in length, the spectroscopic binaries have short periods, reckoned in some cases in days or hours even. If the orbit of a very close binary is seen edge-on, the light of the two stars will coalesce twice in every revolution. Halfway between these points, there are 2 times when the two stars will be moving, one toward the Earth and the other from it. At all times, the light of the star, insofar as the telescope shows it, proceeds from a single object. Now, the photograph of the star's spectrum at each of the 4 critical points above indicated. In the first pair, the lines are sharply defined and single because at conjunction, the stars are simply moving athwart the line of sight, while at the intermediate points, the lines are double. Doppler's principle completely accounts for this. The light from the receding companion is giving lines displaced toward the red, while the approaching companion yields lines displaced toward the violet. Mizar, the double star at the bend of the handle of the Great Dipper, was the first star to yield this peculiar type of spectrum, and the period of its invisible companion is about 52 days. The relative velocity of the components is 100 miles a second, and, applying Newton's law, we find its mass exceeds that of the Sun 40-fold. Capella has been found to be a spectroscopic binary, also the pole star. Spectroscopic binaries have relatively short periods, one of the shortest known being only 35 hours in length. It is in the constellation Scorpio. Beta Aurigae is another whose lines double on alternate nights, giving a period of 4 days, and the combined mass of both stars is more than twice that of the Sun. The catalog of spectroscopic binaries is constantly enlarging, but thousands doubtless exist that can never be discovered by this method, as is evident if their orbits are perpendicular to the line of sight, or nearly so. The history of spectroscopic binaries is one of the most interesting chapters in astronomy, and affords a marvelous confirmation of the prediction of Bessel, who first wrote of the astronomy of the invisible. Find a star's distance by the spectroscope? Impossible, everyone would have said, even a very few years ago. Now, however, the thing is done, and with increasing accuracy. Adams of Mount Wilson has found, after protracted investigation, that the relative intensity of certain spectral lines varies according to the absolute brightness of the star. Indeed, so close is the correspondence that the spectroscopic observations are employed to provide, in certain cases, a good determination of the absolute magnitude, and therefore of the distance. To test this relation, the spectroscopic parallaxes have been compared with the measured parallaxes in numerous instances, and an excellent agreement is shown. The new method is adding extensively to our knowledge of stellar luminosities and distances, and even the vast distances of globular clusters and spiral nebulae are becoming known. In fact, but few departments of the old astronomy are left which the new astronomy has not invaded, and this latest triumph of the spectroscope in determining accurately the distances of even the remotest stars is enthusiastically welcomed by advocates of the old and new astronomy alike. End of chapter 20.